Picture this. You're standing in a machine shop in 1965, watching mechanics tear down an engine that just ran for 3,000 hours straight. No shutdowns, no maintenance breaks, just continuous, relentless operation at full power. The pistons show barely any wear. The bearings look like they could go another 1,000 hours. This wasn't some miracle of engineering luck. This was a Detroit diesel two-stroke designed for tanks, and it was about to revolutionize an industry that had no idea what was coming. I'm sure most people don't realize that some of the most reliable engines ever built weren't designed for trucks or cars or even industrial equipment. They were designed to power 60-ton tanks through desert sand, Arctic tundra, and everything in between. These engines had one job: don't fail when lives depend on you. And when Detroit Diesel's military power plants found their way into civilian applications, they brought something the competition never saw coming: the ability to run harder, longer, and meaner than anything else on the market. This is the story of how Detroit Diesel's tank engines didn't just compete in the civilian market. They dominated it by doing something nobody else could match: refusing to die. These weren't just tough engines. They were engines built to survive nuclear warfare. And when you put that kind of engineering into a commercial application, you get results that seem impossible. Competitors would watch their carefully engineered motors fail after 1,500 hours of hard use. Meanwhile, Detroit's tank engines were just getting broken in, and to understand why these engines were so revolutionary, we need to travel back to 1938. The U.S. Army had a problem. Their tanks were using adapted aircraft engines and modified truck power plants, and they kept failing in combat conditions. Sand destroyed air filters in North Africa. Cold seized engines in European winters. The Army needed something that could handle temperature swings from -40 to +130 degrees Fahrenheit, operate at angles that would starve normal engines of oil, and run on whatever fuel happened to be available: diesel, kerosene, even jet fuel in a pinch. And General Motors' Detroit Diesel Division got the contract, and they approached it differently than anyone expected. Instead of modifying existing designs, they started from scratch with one principle: assume everything that can go wrong will go wrong, then engineer around it. The result was the 6V53, 6V71, and eventually the 8V71 series, two-stroke diesels that broke every conventional rule of engine design. Here's where it gets interesting. While everyone else was building four-stroke engines for efficiency and refinement, Detroit went with two strokes. Not because they were smoother or quieter. They weren't. They chose two strokes because they have fewer moving parts. Fewer parts meant fewer failure points. In a tank, when your engine quits, people die. Simplicity wasn't just elegant engineering, it was survival. And the specifications of these engines were built around extremes. The 6V71, one of the most successful variants, displaced 426 cubic inches from 6 cylinders. But displacement was just the beginning. The engine featured a 17:1 compression ratio, significantly higher than most diesels of the era, which ran 14:1 or 15:1. Higher compression meant better cold starting, crucial when you're trying to fire up a tank in a Russian winter. The engine produced 238 horsepower at 2,100 RPM in naturally aspirated form. But here's the key: it could maintain that output indefinitely, not for an hour, not for a shift. Forever, as long as you kept feeding it fuel and oil. And the engine block was cast from high-strength gray iron with wall thicknesses that seemed excessive by civilian standards. We're talking about main bearing supports that were 2 inches thick. Cylinder walls were 375 inches, nearly twice what you'd find in a commercial truck engine. The crankshaft was forged from 1045 steel, heat-treated to a hardness that could withstand direct impact from shrapnel. Each connecting rod was shot-peened to eliminate stress risers, a process usually reserved for aircraft parts. and engine, but the real genius was in the cooling system. Detroit engineers knew that battlefield conditions meant inconsistent maintenance. Radiators would get clogged with mud. Coolant quality would vary from proper antifreeze to whatever water was available. So they designed the engine with massive coolant passages, some over an inch in diameter. They added bypass valves that would open if passages became restricted. The water pump was designed to move 120 gallons per minute at full speed, 3 times what a comparable civilian engine used. Overkill? In a truck, maybe. In a tank taking fire, it was the difference between making it home and becoming a stationary target. And the lubrication system was equally overbuilt. Oil pressure ran at 50-60 psi compared to 30-40 psi in civilian engines. The oil pump could circulate 60 gallons per minute. Every bearing surface was designed to maintain a film of oil even at extreme angles, up to 60 degrees of tilt in any direction. Detroit's engineers tested this by running engines tilted until the oil pickup was exposed, then measuring how long the engine could run before bearing damage occurred. The answer? 45 seconds at full power. Conventional engines lasted less than 10. Now here's where the story takes an unexpected turn. In 1965, the Vietnam War was escalating and military production was taking priority. But Detroit Diesel had excess capacity for these engines, and someone in management had an idea. What if they offered these military spec engines to civilian customers? Not detuned versions, not adapted designs, the exact same engines going into M113 armored personnel carriers and M60 tanks. The trucking industry's reaction was skeptical. These engines were loud, really loud. At idle, a 6V71 produced 95 decibels. At full power, it screamed at 110 decibels. They were dirty, producing the characteristic blue-gray smoke that two-stroke diesels were famous for. They consumed more fuel than four-stroke competitors, about 15% more for the same power output. By every metric that mattered to fleet managers, these engines should have been failures. But then, something unexpected happened. Logging companies in the Pacific Northwest started buying them. These operations ran equipment 24 hours a day in conditions that destroyed conventional engines. Dust, heat, overloading, the kind of abuse that would kill a normal engine in weeks. The Detroit tank engines didn't even notice. One logging company in Oregon reported running a 6V71 for 8,000 hours between rebuilds. The industry standard was 3,000 hours, and N-word spread fast. Mining operations in Nevada started specifying Detroit tank engines exclusively. One copper mine documented a naturally aspirated 6V71 that ran for 11,000 hours, powering a conveyor system. It never shut down except for oil changes. When they finally tore it down for inspection, the cylinder bores still showed the original crosshatch pattern from honing. The bearings measured within factory specifications. The marine industry took notice next. Fishing vessels operating in the Bering Sea needed engines that could run wide open for days while dragging nets. Engine failure meant more than lost revenue. It could mean death in those waters. The Coast Guard documented multiple rescues where vessels stayed afloat solely because their Detroit engines kept running despite catastrophic cooling system failures. One famous case involved a trawler that ran a 6V71 for 6 hours with no coolant after hitting ice that punctured the radiator. The engine seized eventually, but it got them close enough to shore for rescue. Try that with any other engine. The competition was baffled. Caterpillar's 3306, a comparable 6-cylinder diesel, made similar power with better fuel economy. Cummins' Big Cam series was quieter and cleaner. Both companies marketed their superiority in every measurable category. But they couldn't match one thing: the ability to take punishment that would destroy their carefully optimized designs. The secret was in design philosophy. Caterpillar and Cummins built engines for efficiency within expected parameters. Detroit built engines for survival beyond any reasonable expectation. Every component was designed with what military specifications called Harris casualty radius, the ability to continue functioning even when surrounding components failed. If the water pump bearing failed, the shaft was designed to keep spinning on the seal surface for hours. If the turbocharger died, the engine would automatically adjust timing to run naturally aspirated. If the governor failed, mechanical limits prevented overspeeding. The numbers tell the story. In heavy equipment applications from 1965 to 1975, Detroit's tank engines captured 47% of the market, despite being more expensive, louder, and thirstier than competitors. In marine applications, that number reached 62%. In military conversions for civilian use, it was essentially 100%. Nobody else even tried to compete in that space. But perhaps the most impressive demonstration came from an unexpected source. In 1968, a drag racing team decided to see what would happen if they turbocharged an 8V71 beyond all reasonable limits. The stock engine made 318 horsepower. With massive turbochargers and custom injection pumps, they pushed it to 2,400 horsepower. The engine block, completely stock, handled it. They ran dozens of passes down the quarter mile, launching a 3,000-pound dragster to 180 miles per hour in under 8 seconds. The only failure? The clutch exploded. The engine wanted more. The real advantage became clear in total cost of ownership. A Caterpillar 3306 might cost $8,000 in $1970. A Detroit 6V71 cost $11,000. But the Caterpillar needed a major overhaul at 3,000 hours, costing $4,000. The Detroit could run 8,000 hours before overhaul. When you factored in downtime, the Detroit was actually cheaper per operating hour despite burning more fuel. The engine's tolerance for alternative fuels became legendary. The military specification required operation on 6 different fuel types: DF1, DF2, DFA, JP4, JP5, and JP8. But operators discovered they would run on almost anything combustible. Used motor oil mixed with gasoline? It would run. Kerosene mixed with automatic transmission fluid? No problem. One mining operation in Alaska ran their entire fleet on waste oil from hydraulic systems, filtering it through bread flour and mixing it with 10% gasoline. The engines didn't care. And temperature tolerance was equally impressive. Standard commercial engines were rated for operation between -20 and +110 degrees Fahrenheit. The Detroit tank engines were tested from -65 to +145 degrees. In actual service, they exceeded even these extremes. Seismographic crews in Antarctica operated 6 V71s at -75 degrees, starting them with ether injection and letting them run for months without shutdown. Oil platforms in the Persian Gulf ran them in engine rooms that reached 160 degrees. They just kept running. The maintenance intervals seemed impossible by civilian standards. Oil changes every 100 hours in tanks became every 500 hours in civilian use. Air filter changes went from daily in combat to monthly in construction sites. The engines were designed for teenage soldiers to maintain with basic tools under fire. When professional mechanics got their hands on them in proper shops, they could keep them running indefinitely. The cylinder configuration itself was a masterpiece of battlefield engineering. The V configuration meant a lower profile, critical in a tank where height made you a target, but it also meant better access to components. Every fuel injector, every valve, every gasket could be reached without pulling the engine. You could rebuild a cylinder head in the vehicle. Try that with an inline 6.N Orchgen. The fuel injection system was purely mechanical, no electronics to fail from electromagnetic pulse or moisture. The injector pump was gear-driven directly from the crankshaft, eliminating belts that could break. Each injector was a self-contained unit that could be swapped in minutes. The injection pressure of 3,000 psi was high for the era, ensuring complete combustion even with contaminated fuel. As Detroit's testing procedures were brutal, even by military standards. Every production engine endured a 100-hour break-in at varying loads and speeds. Then came the punishment test, full power for 500 hours straight. Any engine showing unusual wear patterns triggered a complete batch inspection. The rejection rate was 3% compared to 0.5% for civilian engines. Detroit simply held them to a different standard. The turbocharger installations were particularly clever. While competitors used single large turbos, Detroit often used multiple small units. If one failed, the others kept working. The Marines documented M113 armored personnel carriers completing missions with 2 of 4 turbochargers destroyed by shrapnel. The engines automatically adjusted fuel delivery to prevent overfueling, maintaining 70% power on the remaining turbos. But here's the kicker. These engines weren't just tough. They were infinitely rebuildable. The cylinder liners were replaceable wet sleeves that could be swapped in the field. Bearings were available in multiple oversizes, allowing crankshaft journals to be reground multiple times. One documented example involved a 6V71 that went through 7 major rebuilds over 40 years, accumulating an estimated 65,000 operating hours. Ship of Theseus paradox aside, the basic block and crankshaft were still original and unsent. The sound of these engines became legendary. The characteristic Spence Detroit knock mom wasn't a defect. It was the result of high injection pressures and rapid combustion. Veterans could diagnose problems by sound alone. A slight change in the exhaust note might indicate a failing injector. A different rhythm suggested valve recession. Mechanics who worked on them developed an almost mystical ability to predict failures days before they occurred just by listening. The commercial success triggered an unexpected problem for Detroit Diesel. Military contracts required certain production capacity be reserved for defense needs, but civilian demand was exceeding supply. The solution was typical Detroit pragmatism. They licensed production to other manufacturers, but required them to maintain military specifications. Stewart and Stevenson in Houston built them for oil field equipment. General Motors Defense in London, Ontario produced them for export markets. Every engine, regardless of who built it, met the same military standards. And its environmental regulations in the 1970s should have killed these engines. 2 strokes are inherently dirtier than 4 strokes, burning oil by design and producing higher particulate emissions. California's Clean Air Act targeted them specifically. But Detroit engineers performed another miracle. They developed a bypass blower system that reduced scavenging losses, cutting smoke by 60% without sacrificing power. They added exhaust gas recirculation before it was mandatory. They made the dirty engines clean enough to survive another decade. The engines found their way into unexpected applications. Television broadcast trucks used them for generators because they could run continuously during multi-day remote broadcasts. Carnival rides specified them because they could handle the constant load changes of starting and stopping. Ski resorts used them for grooming machines that operated all night in sub-zero temperatures. Nuclear power plants installed them as emergency backup generators, trusting them with reactor cooling when the grid failed. And in racing applications pushed the boundaries of possibility. Tractor pullers discovered that 8V92 blocks could handle 5,000 horsepower with proper reinforcement. Offshore powerboat racers ran twin turbocharged 12V71s, making 1,400 horsepower each, launching 40-foot boats to 140 miles per hour. Land speed record attempts at Bonneville used supercharged and turbocharged 12V92s, pushing 3,000 horsepower. The engines that were designed to move tanks at 30 miles per hour were pushing vehicles past 300 miles/an. The Soviet Union tried to copy them. They acquired several through third parties and reverse-engineered every component. Their version, the D-12, was dimensionally identical but failed consistently. They couldn't replicate the metallurgy. Detroit's heat treatment processes, developed over decades, created grain structures that looked simple but required precise temperature control within 2 degrees over hours-long cycles. The Soviets' engines cracked cylinder heads and threw rods at a third of the power output, and then reliability statistics from insurance companies revealed the true advantage. Equipment powered by Detroit tank engines had failure rates of 0.3% per thousand operating hours. Caterpillar averaged 0.8%. Cummins was 0.7%. The difference seemed small until you operated a fleet of hundreds of units. For a mining company running 200 pieces of equipment, it meant 10 fewer breakdowns per year. At $50,000 per day in lost production, that difference paid for the entire fleet's higher fuel consumption. That's the engine's simplicity enabled field modifications that would terrify corporate lawyers today. Operators routinely turned up injection pumps for more power, advanced timing for better fuel economy, or modified governors for different operating speeds. The engines tolerated abuse that would scatter competitors. One documented case involved a logger who accidentally filled his 6V71's cooling system with hydraulic fluid instead of antifreeze. He ran it for a week before noticing. The engine survived with no damage. In Alaska's oil pipeline construction, Detroit-powered equipment operated in conditions that challenged every assumption about mechanical limits. Temperatures hit minus 60 degrees. Hydraulic fluid turned solid. Steel became brittle as glass. But the Detroit engines started and ran, heating hydraulic systems with their exhaust, providing the warmth that kept other equipment alive. When the pipeline was completed, contractors calculated that Detroit-powered units had 40% less downtime than any other brand. NN Marine applications revealed another advantage. Salt water destroys engines through corrosion, but Detroit's thick castings and generous material allowances meant they could lose significant material to rust and keep functioning. Shrimp boats in the Gulf of Mexico ran 6 V71s with cooling passages so corroded you could see daylight through them. The engines didn't care. They kept pushing boats through hurricane seas when prudent captains would have turned back. The military never forgot these engines' civilian success. When designing specifications for the next generation of combat vehicles in the 1980s, they specifically referenced the commercial reliability data. If an engine could survive Alaskan logging and Gulf Coast shrimping, it could handle combat. The Bradley fighting vehicle's engine requirements explicitly stated high civilian proven reliability equal to or exceeding Detroit Diesel Series 71 in commercial service. 10N parts availability became a strategic advantage. Because the military stockpiled components for decades of potential conflict, civilian operators could find parts anywhere. Need a crankshaft for a 1965 6V71 in 1995? The military had warehouses full of them. Injectors, pumps, gaskets, everything was available new old stock at surplus prices. Competitors' parts became obsolete after 10 years. Detroit parts were eternal. The engines developed personality cults. Operators named them, painted them, decorated them like shrines. In Australian mines, crews would bet on which Detroit would outlast the others. One famous 8V71 called Churchill's Iron Miking ran for 19,000 hours in a haul truck, survived 2 vehicle fires, and was eventually retired to a mining museum still in running condition. The plaque reads, "This engine refused to die. We gave up first." By the 1980s, emissions regulations and fuel economy demands We're ending the era of pure mechanical reliability. Electronic controls, while more efficient, introduced complexity that military specifications avoided. But Detroit had proven something important. When you engineer for the absolute worst case, when you assume everything will go wrong, when you build for survival instead of optimization, you create machines that transcend their specifications. Mine, the last military spec Detroit two-stroke, came off the production line in 2000, ending a 62-year run, but thousands still operate worldwide, maintained by mechanics who understand what they represent. These weren't just engines. They were a philosophy rendered in iron and steel, the idea that with enough engineering margin, enough redundancy, enough sheer mechanical willpower, you could build something essentially indestructible. Ancient modern engines are marvels of efficiency, computer-controlled common rail injection, variable geometry turbochargers, selective catalytic reduction, technologies that make 500 horsepower from 4 liters while meeting emission standards the Detroit engines couldn't dream of achieving. But ask anyone who's run both what they'd want when failure means death, and the answer is always the same. Give me the Detroit. Give me the engine designed for war. The numbers support this preference. As of 2024, the estimated survival rate for Detroit military spec engines built before 1975 is 34%. For comparable civilian engines, it's under 5%. These engines weren't preserved as collectibles. They survived because they're still working, still earning their keep in applications where downtime costs more than fuel. Brazilian logging operations, African mines, Russian Arctic settlements, places where the nearest parts store is 1,000 miles away, and failure isn't an option. What made these engines outsmart the competition wasn't advanced technology or clever innovation. It was the opposite, the deliberate choice to prioritize survival over everything else. While competitors chased efficiency metrics and emission standards, Detroit built engines that would run after nuclear war. That design philosophy, born from military necessity, created something the civilian market never knew it needed: engines that refused to die. Now, the lesson extends beyond engineering. When you design for extremes, normal operation becomes trivial. When you build for battlefield reliability, commercial use is easy mode. Detroit Diesel's tank engines didn't outsmart the competition through sophistication. They won by being too tough to kill, too simple to confuse, and too proven to ignore. In a world obsessed with optimization, they proved that sometimes overbuilding isn't waste. Sometimes it's genius. Today's engines are better by every objective measure. They're cleaner, quieter, more powerful, more efficient. But they'll never match what Detroit achieved with those military power plants. The absolute confidence that no matter what went wrong, no matter how bad conditions got, no matter how poorly you maintained them, they would keep running. That's not something you can program into an ECU or design in CAD. That's engineering philosophy forged in combat and proven in the hardest applications on Earth. The story of Detroit Diesel's tank engines reminds us that sometimes the best solution isn't the most elegant or efficient. Sometimes it's the one that survives when everything else fails. In engineering, as in life, there's profound wisdom in building for the worst case and being pleasantly surprised by normal operation. These engines outsmarted the competition not by being smart, but by being too tough to care about being smart. And in the end, that made them brilliant. What's the toughest engine you've ever encountered? Drop your stories in the comments below. If you enjoyed this deep dive into military engineering's civilian conquest, hit that subscribe button for more tales of mechanical legends. Until next time, keep those engines running, especially if they're Detroit's.